So here we're going to introduce the idea of an activation energy, and we'll use carbon as an example and an activation energy diagram that compares graphite, one form of carbon, and diamond, another form of carbon. So these both have the same chemical formula, and that is C. And well, we'll just erase this and draw a diagram. So this is an activation energy diagram. We have energy increasing upwards, and then to the right, we have what we can call the reaction progress, and that'll be something moving to the right. And we'll take a couple of pressure and temperature conditions. To start with, we'll look at the case of pressure is equal to 1 atmosphere and the temperature is something close to room temperature, 20 degrees centigrade. So at low temperatures and low pressures, graphite is the stable form of carbon. And so the way that would plot out just qualitatively on this diagram is that if we put graphite on the left and diamond on the right, if we have an energy well here, then graphite would be sitting at this lower energy, and then diamond would be perched up here at some higher energy. But we can connect these energy curves, and we can do so thinking about how diamond might convert to graphite. So if you have some jewelry or you've got a mineral collection that includes some diamonds, is it possible that this diamond that is sitting up here at much higher energies than graphite would spontaneously convert to graphite? So we've got the energy of diamond here, and that's at a much higher potential energy than the energy of graphite here. Why doesn't diamond just spontaneously make its way into the graphite structure? Well, the reason why is because we have this so-called energy barrier, and that energy here, we'll call it E sub A, is the so-called activation energy. And that is the energy that you need to put into the system to take all those very strong carbon-carbon covalent bonds in a diamond, break them apart. It's going to take a huge input of energy, and then once you do that, there will be a lot of energy released as they reform into a graphite-type structure. So graphite is definitely the stable form. It's sitting here at lower potential energy, but graphite is not readily obtained from diamond, at least not spontaneously, because of this very large energy barrier. Now, you can help graphite move over that energy barrier if you heat it up. So if you take the system from 20 degrees up to, let's say, 1,000 degrees or some other higher temperature, then you're going to have a greater chance of having it climb over that energy barrier and then falling into this lower energy well. Let's take another system. Well, rather the same system, but at different conditions. So we have another activation energy diagram here, again with E moving to the right, reaction progress, we'll call it R moving to the right, E going up. We'll leave graphite on the left and diamond on the right as we did before. But let's say our conditions are P equals 50 kilobars. We'll leave temperature the same as we did in the last diagram at 20 degrees centigrade. For background, 1 bar is about 1 atmosphere. So when we talk about a 50 kilobar pressure, that's about 50,000 times atmospheric pressure. Well, in this case, diamond is now going to be the stable phase. It'll be sitting here perched at a lower potential energy, and it'll be graphite that will be perched at a higher potential energy. And so it is graphite that should spontaneously convert to the lower energy form of diamond. And as it ends up, the activation energy barrier is a little bit lower, so it'd be a little bit easier to make that conversion. And anybody who works in a lab where you take graphite and compress it to very high pressures, it's not that hard to make diamond. You can do so, but you still have some covalent bonds here that you have to break, and they'll have to be rearranged before they can release that energy as they reform to make the graphite structure. So this is here that, again, this activation energy barrier. So that's E sub A. It's the amount of energy you need to put into the system to get this high energy state over the hump so it can collapse into this lower energy state. And we will save the details for another video, but this plays into the so-called Arrhenius equation, where a rate constant K can be related to a frequency factor multiplied by E raised to the minus e to the sub a over RT. R is the gas constant when we count things in molar units. T is temperature. And then this is the activation energy that we have talked about in the previous diagram. So that is the activation energy barrier. And we can relate K, this rate constant, to that activation energy. And there is this other factor here, A, usually referred to as a frequency factor or an attempt factor, a way to think about, in a sense, in a very kind of colloquial way, how many times will atoms make the attempt to jump over that activation energy barrier to fall into that lower energy potential energy well. So you can think of it as an activation energy barrier, and then how many times do the atoms try to make that jump. But we'll deal with those details in a different video.